communication engineering and technology. So as far as why we have considered this webinar, I should say, because now it is not a seminar, everything is being conducted online, so it has become webinar now. So why this particular webinar is important to be mentioned at the starting. So as we all know that statistics is an important tool in our lives now. So it is used in the analysis of random behavior. For example, be it a cricket match, be it a football match, or be it a medical line, be it a communication engineering, everywhere there is a randomness. Even there is a randomness in the life as well. So we can say that randomness is the basis of life. Randomness is the basis of science and technology also. So it cannot be, life cannot be made perfect unless and until randomness is removed or seized or reduced to a certain extent. So it is important to know what are the tools. So from this point of view, the tools were introduced by various researchers for the analysis of random behavior. For example, astrology, I consider astrology is also a tool to reduce the randomness in the life. Similarly, there are various tools in the Excel, statistical tool, which is being used in the Excel by the MATLAB for analysis of random behavior. The objective is one, that is how to reduce the randomness and optimize the performance. So in this respect, the communication engineering is not an exception. For example, in communication engineering, there are two major enemies. One is noise and other is distortion. So what does noise do is it increases the randomness, and distortion further worsens the performance of the communication system. So the question is how we can, what are the tools that we can use in communication engineering to reduce this randomness and increase the performance. With that idea in mind, this particular webinar was conceived, and I'm thankful to our speaker, Professor Dr. Rajiv Kapoor. I'll introduce him. He has, first of all, I thank you for giving the consent to be part of this webinar. And let me introduce him first, and we will start, we will take important knowledge from him. So Professor Rajiv Kapoor is basically a professor in Department of this Delhi Technological University, EC department. And he had been ex-principal in Ambedkar Institute of Advanced Communication Technology and Research, that is in Gita Colony, New Delhi. And he has his interest area includes vision and speech-based tracking, machine learning, activity recognition, vision speech-based signal processing, pattern recognition, and cognitive radio. He has more than 65 papers in SCI expanded or Scoopers index journals. This is really a great achievement. So he has 54 papers in proceeding in international conferences, and 11 patents to his credit, and some of the patents are in publication stage. He has written, Professor Rajiv has written 7 books, and it is important to mention that these books are in the reputed publishers like Pearson and Springer, and 4 books is on GATE series by Pearson. GATE, how to crack GATE examination. This is published by Pearson. Dr. Kapoor has 2 sponsored projects by Government of India, and with the total worth of approximately 80 lakhs. So this is a very short introduction of Dr. Rajiv Kapoor. And sir, thank you very much for being part of this webinar.
Yeah, welcome.
Yeah. So please, sir, enlighten us about today's webinar and topic.
Yes, definitely. So let me first try to share the screen so that, and you just keep on telling me whether the screen is now, whether you can see that or not. Okay.
Sure, sure.
Just let me try this. So I'm trying to share the desktop.
Okay.
I think that's the best option.
Mm-hmm.
Hello, sir. There is an option called share screen at the top of at the bottom, sir.
Okay, where is that?
So there's a green button at the bottom of your screen.
Yeah, that's what I'm doing.
Sir, I have given the permission. You can share it now, sir.
Yeah. Okay, just 1 minute. It's written over there. Who can share?
So you can, because you are co-host, sir. You just try. You just try sharing, sir.
Okay. Acha, it is already shareable now. There is no need to.
Your screen is not visible, sir.
Not visible. No, just 1 minute. Now it's asking for share desktop. Is it? Can you see this now?
No, sir, not yet.
Not yet.
Rajesh sir, if you mail me your PPT, I can share and I can play it here.
That's better. That's better. I will send you.
Yeah, amit.ahuja@mit.ac.in. I'm writing on the chat box.
Yeah. Still, I can see.
Pardon, sir?
I'm sending you on the WhatsApp.
Okay, right.
Yes, I have already sent.
Yeah, I have received. I'm trying to open it on my laptop.
Please.
Is this visible, Mr. Vishwash?
Yes, sir. It is, sir. Fine, sir.
Okay, wonderful. Rajesh sir, you may please continue now.
Yeah, please. Thank you very much.
Thank you, sir.
So you were trying to introduce the topic, and it was rightly that there is a lot of randomness. especially because here the audience is mostly related to the electronics and communication engineering branch. And we all know that communication engineering is one of the very, very important uh, part of the electronics and communication engineering branch. So that's why my objective today is to convey you uh, the use of the application of communication, the statistics in the communication engineering. And what I have done is I have taken this radar as a case study, especially the MTI radar over here. So when we talk about the communication engineering and technologies, it means it's not just the what we say the hardware or the baseband communication. What matters in addition to that is the how you are going to transmit and how you are going to and what all data, what all redundant data, how many times, and do all these things matter to us when we try to uh, have a very reliable communication. So, dear all, I will like to now move to the second slide where I start with my topic for today. So please move to the second slide. This can I also move in the classes is first to take the problems so that we may understand we may appreciate and we may get motivated to understand the topic. So that's why I have taken up some major problems, and because many of you will be trying to take up some research also in this particular field, so it will be good for you to know about the problems existing in the detection process. Now, the very first problem is the should reach to the destination. That is what is needed. So we all understand, we have understood the information theory. But in information theory, a lot of stress has been given to maximize the information. But the channel is random, we all know. And if we take up any kind of deterministic model, that may not take us near to the realities, right? So therefore, this particular topic of maximizing the information content under the various constraints existing with the channel. See, it's really difficult to understand the channel. It is extremely difficult to model the channel. Therefore, until we understand, we cannot model it. If we take some already existing model that may or may not fit into the channel which we are trying to optimize. But then question arises, how do we do it? So there are two things you have to keep in mind, that for any kind of maximization or minimization problem, you need to have your objective and you need to have some constraints. If you know the constraints existing for an objective, then you can find the best possible path. Now here the best for you is to maximize the information. Similarly, so let's, because I'm trying to raise questions. The second question transmitted in our always an objective that we need to minimize the error. Hello, am I audible? Hello,
Yes, sir.
am I
You are
audible?
yeah. Yes, sir. You are audible.
Okay.
In between, there was some problem.
Okay. Okay. Yeah, I will move on. So minimizing the error between transmitted and detected signals is another big issue. See, how can we minimize the error? When the signals are random, it's the probability of error what we can try to understand. And we know that Shannon has already explained that the probability of error is dependent upon the probability of miss and the probability of false detection. This probability of miss and probability of false detection depends upon and which is more harmful for the communication system, right? So this is the second question. Third one which comes to our mind is that we have studied meshed filters, but how can we have the optimum design of the receiver using a meshed filter? Mesh filter can be used anywhere because the type of signal is known to you. But is it possible to have the best possible receiver by using just a meshed filter? Or we can say that the meshed filter is just a beginning and there is a lot more required to actually design the receiver. So what is that? That is the third question. There is another problem which is of denoising. We know that channel has only one issue, only one problem, that it introduces noise to the transmitted signal. And because the noise is white and sometimes some people say that it is Gaussian. See, up till you say it is white, it is understandable because this is a generalized meaning given to the noise. But when you say it is Gaussian, then that means you know something. It means you know about the noise itself. So it means there must have been some technique existing through which we could model the noise also. Okay, so that's why denoising is a concept which can be taken as a research component, and you can link it up by understanding the kind of noise, by modeling the noise. Yes, please, can we move to the next? Now I'm trying to classify we thought of that there will be sometimes some optimum receiver and we need to work for it. Now, how can we classify those so-called optimum receivers? Now, the first concept based on which we can classify is the maximum average signal to noise ratio criteria. So, if the signal to noise ratio is increasing, it means it's going towards the optimum. Second criteria can be the maximum peak signal to noise ratio. It can be average or peak, but there will be always a noise in the background. So how can we have the peak signal to noise ratio as possible as maximum, considering that there is a noise in the background? Right? So this is another way of looking at the optimum receiver. The third criteria can be the MAP criteria, which is known as the maximum a posteriori criteria, where you know nothing about the signal. You have no knowledge, of course, about the received signal, and you have no knowledge about the transmitted signal also. I give you an example of this. Consider, just think of that there is a wall. On one side you are standing, on the other side your friend is standing. Your friend is carrying a large number of rubber balls. Your friend will throw the ball and you have to catch it. But the problem is that you can't see your friend. So this means that you do not know from which side the ball will come. So it's a difficult issue. There is another scenario. Let's think of a football ground where penalty stroke has been granted to one of the team, and some good person, some good player of that team has to take the penalty stroke. But that person is in front of the goalkeeper and can see him directly. Only problem with him is that because the shooter of the ball will shoot the ball at a very high speed. So therefore, he has to match his understanding and visibility with the speed of the shooter. So this is where the crux is. So it means in one case you can see something, in other case you can't see anything. So you never know from where the ball is coming, and you have to be prepared. But the best point is that in the case of wall, the ball will not come very fast, because you have to throw the ball from upside of the wall. So that's why this criteria is called as the MAP criteria. In the second criteria, where I had taken an example of a football ground situation, the situation which I mentioned to you is called as the ML criteria. These are two very popular algorithms. Now let's talk about the fifth classification. That is maximum information transmission criteria. We know it, we have already mentioned it, but There is something else also along with it. Maximum information and minimum error rate criteria. Now, question arises that maximum information, is it related directly to the minimum error? So if error is minimum, you are getting the most part of the signal as it is. So there may be signal also and there may be information also. So there will be signal and there is a redundant signal also along with it. So error might be anywhere. So how can we optimize? How can we think of if, for example, the redundant bits which are transmitted along with the signal component, if they have the errors, we should still be able to detect it. So it means this is somewhere related to the error detection and correction also. Yes, please kindly move to the next one. There is another way of looking at the classification, like mean square error criteria for filtering and for prediction. Now here also we take the mean of the square, but the signal is random. So here the mean means ensemble average in general. The question arises, how many types of averages can possible? Why only ensemble? Why not time average? Why not statistical average? Why not moving average? Why only ensemble average? Right? So this is directly related to the study of the random signal theory. So I'm not going much into the depth of that. I assume that all of you are aware of this subject. So, but it can be used for the filtration and for prediction purpose. So it means filters can be predicting filters also. So let's take a detection problem where the received signal is always distorted. It's not possible that there is no distortion. Otherwise, the channel will be deterministic or a noise-free channel, very hypothetical channel. So if there is a signal distortion, it means the channel will have the non-linear, non-ideal characteristics. So again, the classification can be based upon how to understand the non-linearity of the channel. How much non-linear the channel is. How do we find it out? So this becomes one of the major classification property. Next one is the desired signal where, let's say, is known to us. Its shape, amplitude, and arrival time. And we know that desired signal and the observed signal are two different signals. So observed signal is a random process because of the noise. So now we have to think of how these issues, classifications can be understood. So here comes the fulfillment of our objective, and that's where the topic comes into picture. And we can take the help of statistics to solve these issues. Let's please go to the next one. So what I've done is, in this presentation, I have taken and solved all the questions also. Because I know generally in these presentations, people attend the presentation, but they hardly understand until there is a mathematical solution. So what I have done is, I have solved mathematically the problems which I have considered, and then we have tried to I have tried to solve it in the PPT itself. So let's move from the very, very basic. Even if somebody has not prepared well for the communication, he can also understand it. So let there be a signal ST which has been disrupted by the noise NT, and the received signal is YT. The only situation which is known to us is that it is a digital signal. And digital signal can be expressed in two situations. The first one is the presence of signal, and the second one is the absence of signal. So what I'm doing is, I'm calling and representing it as two hypotheses. The no signal situation is represented as null hypothesis. So no signal means there is no signal at all. So it means YT becomes equal to NT, absence of signal. And the presence of signal will have the original equation, YT is equal to ST plus NT. So I'm calling this as a hypothesis 1. Please go to the next one. So what I'm trying to do is, now before I take up this, you need to just recall a simple Bayes theorem which everybody studies at the time of BTech. So based on that, but still I will try to make it clear if somebody is not able to recall it. I will try to make something clear to you. So let's take the first task of taking a decision based upon the presence and absence of signal. We know when the signal is present, it will definitely have a noise. If the noise is too much, then in that case, signal will lose its identity. H0 is absence of signal hypothesis, and H1 is the hypothesis for the presence of signal, but noise. So H0 is only noise, and H1 is signal plus noise. So let's take a decision that the result will be hypothesis 1 if the probability of hypothesis 1 when Y has been received is greater than the opposite part. Similarly, H0 is the final hypothesis when the probability of no signal hypothesis, when the received signal is only containing noise, might be only containing noise, because you are never aware of what the Y contains, whether Y has only NT or ST plus NT is not known to you. So therefore, we can only say that the hypothesis 0 and its probability when something has been received, if is greater than the probability of hypothesis 1 when the same signal has been received, then it will be H naught hypothesis. So this means further that we will consider the Y signal as sometimes as once as H naught and the second time as H1. Then we compute the probabilities and compare them. But let's say, what these probabilities are. The probabilities are a posteriori probabilities. And I have already told you that a posteriori probabilities are the most difficult to understand. There is hardly anything known to you. I further take one more example because as I have seen, until you take the examples, it's really difficult to understand these studies. Now what I'm doing is, let's say you have just passed out. Student, let's say BTech, you passed out with flying colors, and then you got a job also, and you got the first salary, and you want to send something to your mother or father. Now what happened is, you sent something, purchased and sent something through courier. Now there are two situations. The first situation is that you sent through courier and did not inform your mother or father. Let them receive it. So your parents do not know about whether you have sent anything or not. Right? Second situation is that you sent it through the courier, then you gave a call to your mother, you told your mother that I have sent you this. This is from my first salary, and these are the courier details. These are the courier details. So, in the second case, you will see the mother will call the courier person and will try somehow to get the courier at the earliest possible. So it means in the second case, the probability of error has reduced to a large extent because by telling something in advance has ensured that the information will be delivered at the destination. Right? But the question arises how much and what you know about that. That is a difficult part. Well, for the time being, because we are not doing research in that portion, we are using statistics, right? So therefore, I will come back to my statistics part. So I'm using a Bayes theorem, okay? And through this Bayes theorem, if you see all these line by line computations, because I know what is P1, I know what is P naught, I know what is Py over 1, I know what is Py over 0, I also know what is Py, irrespective of X, because I'm getting something. Somebody has sent me the gift. When I receive something, I open it, I know about it. Yes, I do not know anything before I received it. So it means from the known probabilities, Bayes did a wonderful job that it could compute something unimaginable, unknown from something known. So that's the beauty of the Bayes theorem. So let's go to the next slide, please. Now, because this is all step by step, you will see the way I teach in the class, the same thing I'm telling you over here, so that all of you understand in a very, very simple manner. But we know that the P0 plus P1 is maximum going to be equal to 1. So what is this? This is a constraint. But this is known to us. We also know that Py over 1, because 1 is nothing but h of 1, hypothesis 1. Similarly, 0 is nothing but h of naught. So therefore, Py by 1 is equal to Py by h1. And similarly, Py by 0 is equal to Py by h0. So now we acquired some knowledge from here, and we will like to now make changes in the decision rule. So we made a decision rule change. Now it is a division. Such kind of division based decision rule is called as the likelihood ratios. And all divisions, if you want to express in a simple manner as a addition or as a subtraction, you can take the log of that. So that's why these are called as the LRTs, log likelihood ratios, right? So let's go to the next one. So alternative decision rules, we can choose the, no, thing is that, see, we have to decide between 0 and 1. Now we have to insert some hyperplane in between. The left side of that is 0. The right side of that is 1. I call this hyperplane, and the position at where the hyperplane has to be inserted, that is called as the decision threshold. Why not? So this why not is selected in such a manner so that the overall probability of error is minimum. So let's see in the next slides, how do we minimize the probability of error? Yes, please. So probability of false detection and probability of miss can be expressed in a easy way. And we know that the sum of these two will be the total probability of error. So what we do is we compute from here the total probability of error. And for minimization, we use the steepest descent method, right? And then try to minimize it. See what happens. Let's go to the next slide. So you can see we got the hypothesis 1. If this computation of the likelihood function L1 is greater than the L threshold, right? Then it is hypothesis 1. If it is less than threshold, then it is hypothesis 0. Please go to the next one. Now let's try to further, because you have tried to minimize it using the steepest descent. But taking such kind of decision, let's say the enemy has sent the aircraft and you have a radar, and radar, if could not recognize the exact position of the enemy aircraft, your anti-aircraft missile will miss the target. So that will be a big loss to the country. So it means your method has to be risk-free. So how do you minimize the risk? So for that purpose, I have designed a cost matrix where if 1 is transmitted and 1 is received, if 0 is transmitted, 1 is received, 0 is transmitted, 0 is received. See, if the transmitted and the received signal are same, that means it is an error-free signal. There is no error in this. Let's go to the next slide, please. So this is how I represent the hypothesis matrix under when you consider that if the signal and the received signal, transmitted and received, if both are not same, then only it will cost you. Right? If both are different, in that case, it will cost you. So therefore, here you have written H11, H1 for X and Y1, H0 for X and Y0. But if you see the second value, when the X is 1 and Y is 0, it is an error signal. It means 1 has become 0. In the other case, X is equal to 0 and Y is equal to 1. Here also it is an error. So these are the two error hypotheses. Let's go to the next piece. So we compute a cost matrix and we notice that the first, the first value in the cost matrix is 0 and is also 0 along the diagonal, because diagonal is the only place where the signal which has been transmitted is same as the signal which has been received. So therefore, cost matrix can be defined like this. Let's go to the next slide, please. So this is how I write as an integral equation. The same thing I have written, I have tried to solve it and compute the average risk detection value. Let's please go to the next one. So average risk need to be minimized. So it becomes another minimization problem. How can we minimize? By choosing the right place of the threshold. Why not? So what we do is we take the first order PD of the cost matrix with respect to y naught and put it equal to 0. Yes, please. Let's go to the next one. In this particular slide, you will see that now the cost for the wrong signal component which has been received, we are assuming over here that the noise over here is a Gaussian noise, right? Many of you can definitely say and can assume that the noise may not be Gaussian. But what is the reason that in 99% of the cases, in the books we refer to, they always consider Gaussian noise with mean equal to 0. So for the time being, though this is another branch of research, but I'm coming back to first my objective of doing it through statistics. So what we do is we assume that the PDF of the Gaussian noise is Gaussian, and the means are A0 and A1. So now when we try to find out this IT, it will be as shown in the figure itself, the very first equation. So the second equation, if you see, has been derived from the first one only. Okay, so it means we can re-represent this equation in this particular manner. And if you try to solve it in the third equation, it becomes like this. So this is step by step. This is step by step modeling, right? So let's go to the next slide, please. Now, thresholds for Gaussian noise. Further, if you see the computation, calculation by taking log on both the sides to solve the exponential, the equation at the end, if you see the last equation, which gives you the y naught is equal to sigma square and a1 minus a naught log, etc., etc. And see the last part of it, a naught plus a1 by 2, right? This a naught plus a1 by 2 is a statistical average of the two signals, 0 and 1. Now, what is that extra part? This extra part is to move the threshold either in the left or right direction so that our detection becomes optimized. So it means if you have to distinguish between 0 and 1, it's not always the right way that the middle of the two should be taken. Like for example, if A0 is -1 and A1 is +1, then the average of the two will be equal to 0. And this is what we do in general. But in reality, we should do like this. Why not is not a easy equation. It has become complicated because this will give you the reduced form of the probability of error. Next, please. We try to solve this problem of radar-based MTI radar based upon the statistical detection. We realize that we have chosen the steepest descent technique. But is there any possibility of enhancement in the technology with respect to the earlier technique of based upon steepest descent? So here we have another technique called as the multiple observations. Just if, for example, if something, for example, you are driving the car and something is not visible properly. Let's say there is a lot of fog. Because of fog, everything is not visible. So your mind is little shaky. Where drive the car a little slow. So what you do is you try to blink your eyes and see at the destination or the target multiple number of times. So those multiple samples should help you in better detection. So the same process has been used in the radar-based detection also. So here you denote Py of 1 because y is a vector and it has n symbols. Therefore, it becomes P of y1 to yn when 1 has been transmitted. So let's go to the next slide, please. So this is the cost function selection when the number of hypotheses are more than 2. We could know about one more technique by taking more observations. Second new technique is that why not to increase the number of hypotheses? So in each of the slide, I'm trying to give you a new glimpse of a new technique because the time is short. So that's why I reduced those slides. So we can have another way of looking at the hypothesis detection that is called as the composite hypothesis. The composite hypothesis is different from the previous one because if there are, let's say, m parameters, theta 1 to theta m, which are interdependent upon each other, like, for an example, amplitude, frequency, phase, time of arrival, and so many other parameters. In that case, if you compute the likelihood function, you can consider only one at a time. Because if you consider a lot of interdependent functions parameters, then it will be very difficult for you to find out. So this integral can be solved one at a time, right? So then this ratio will give you the likelihood ratio and your objective identification process will improve as a result of the composite hypothesis. Let's go to the next slide. So, transmitted signals in a radar system are the RF pulses. And we have considered noise as a AWGN with mean equal to 0. And I have already raised a question for you to know about why the noise is generally AWGN with mean equal to 0. So if I get later on some extra time, I will definitely try it, because this itself is a big study. When the target is in motion, there is a possibility of signal fading. Another detection issue is that amplitude A, phase phi, time delay T, they are varying continuously. So it means when all of them are varying in a random manner continuously and are interdependent also, so it must be a difficult issue. Then decision circuit has to be an optimized circuit. We should have high detectability, high accuracy, resolution. Now, how is it possible? Probably it is possible through an improvised matched filter. Question arises, how can we improvise the matched filter? What is that which we missed in the matched filter? Another detection issue is the incoherent detection, where the phase at the receiver side might be different from the transmission side. Let's please go to the next slide. So let's try to solve it. We propose a new technique called orthogonal M-Array signals. So what we'll do is we'll try to transmit many signals now, but they will be all orthogonal. So it means if we try to transmit the orthogonal signal, then their detection will be much comparatively easier, because this is the inherent property of the orthogonal signals. So this is one solution. Let's go to the next one. Yeah. So now this is an extension of the orthogonal signals based M-Array process in MTA radar. So here I am proposing a kind of hypothesis detection process. So this is a likelihood function. If the left hand side is greater than the right hand side, this likelihood function, then it is for hypothesis 1. And if it is less than that, then it is hypothesis 0. Yeah, please, let's go to the next one. Orthogonal codes in digital communication are another important. So here I have considered header word codes which are easily representable. To make you understand the concept. Please go to the next one. Now in a radar study, what are the basic signals which are random, and we need to do the proper estimation for that. One is the target size, second is the range, third is velocity, fourth is the signal parameters which vary randomly, and the fifth one is optimum estimation of 3 parameters for coherent and incoherent signals. So these 3 parameters given in the top of the slide, if can be detected for coherent and incoherent signals, that may also lead to the optimum estimation, right? Next, please. So this is how we compute the Bayes estimate and the Bayes risk. The basic concept is same, only the parameters have changed, right? So you can see it is R of A oblique Y, C of A dash comma A. Right, so this is nothing but the cost function, right? So, but this function is valid for the new method which I have proposed you recently. So this kind of risk which we compute through this is a conditional risk. Please go to the next slide, please. So this is how we optimize the cost function. So we notice the mean square variation of A dash, which will be minimum at the del C by del A dash is equal to 0. Because this is the way to find the minima of the function. So if many parameters like A1 to AN have to be simultaneously estimated, and being Y is a vector, in that case we can compute the average risk as I have shown in the last of the slide. Please next go to the slide. There is one more method to tackle this problem that is called as the map estimate for unknown cost function. So when the cost function is also not known, in that case, we can apply the map estimate algorithm, maximum a posteriori algorithm. So I have shown you the computations of how do we apply. Let's go to the next slide. So these are the parameters which can be estimated, like acquisition of carrier frequency and their phases, symbol and word synchronization for digital data, optimization demodulators of AM, FM and pulse modulated analog signals. We can even optimize them. The last one is the optimum filtering. Yes, please, let's go to the next one. So let's try to consolidate in short. We have understood that we learned baseband detection, but it is highly dependent upon the statistics. So statistics is extremely important in case we wish to design the novel kind of receivers. Multiple parameters should be optimized because multiple parameters are difficult to understand. And in case we can optimize them, that will definitely lead to the qualitative reception. And the third point we have to consolidate is that in the communication study, when we try to solve it using the statistics, we have to deal with a posteriori probabilities, which is a little difficult task, but it can be computed in terms of the a priori probabilities. Fourth point is that we are using a lot of optimization techniques in the statistical methods. So they might be having constraint. So these constraints, they not only help in the process of optimization, but also are trouble for the optimization issue. The last is that tracking parameters, which are computed considering. So tracking parameters are computed only by considering one at a time. This is what I had shown you in an equation where there were multiple parameters on which the same transmission depends upon. And while computing the likelihood function, we have to deal with the multiple parameters or the likelihood ratio. So what we can do is we can consider one at a time, considering no variation in the other parameters. So in that case, it will give you the optimum receiver design. Right, so let's go to the next one, please. Few more things we have understood is that the statistical detection is more important when we do not wish to lose a single bit. So it means there has to be some hidden information. So where do we keep this? How does this hidden information help us to have a better detection based upon statistics? So this is one of the things we learned from this study. And the next point is the impenetrable spread spectrum. We have studied spread spectrum in isolation of much of communication. But spread spectrum, if you see, is generally used by the defense for communication purpose, but it can be used in a much better manner if we go for statistical communication. So this will employ intelligent detection process, which is the need for the futuristic detection, because all these statistics is going to be embedded, and that will help us to have a much better communication receiver. Let's go to the next one. So, my dear all, this was a glimpse of the statistics which is extensively used for communication technologies. So, what you can do is, that's why I took actually a limited one which can be covered in this. Otherwise, communication is a very vast topic, and anybody whosoever is interested in doing research can always communicate with me. But just now you can always ask me the questions, please.
Thank you very much, sir. Yeah, it was really an informative session. And as far as I know that this particular portion that you have covered is said to be very difficult, and student has phobia, especially when they come across statistics in communication. But the way you have presented, it has become so simple for all of us, including myself as well. Thank you very much, sir.
Please. And anybody can ask the questions if they wish.
Yes. Participants, please put your question in the chat box if you have any doubt. Okay. So meanwhile, there's some question with me that I would like to ask from you. Yeah. So the first question is the question that you have raised to we people in the starting. That is, why in study we consider AWGN with zero mean?
Yeah. Actually, that's where actually this is one of the research topic. So what we do in general is, at least up to BTech or MTech level, we consider certain constraints related to the peak value, average value, and the average energy value. Keeping these constraints on the channel, if we try to solve and optimize the channel, then it will come out to be a Gaussian function with mean equal to 0. And this is one reason, actually, because this is a very long derivation. So, but I have given you the crux of that. So that will come out to be the Gaussian function.
Can you please repeat, sir, again?
Yeah, if you try to, like, the random channel will have to have an objective of the best information content which gets delivered. So when we have to ensure that content to be delivered at the destination, we put the channel under constraint. The constraints can be, depending upon 1 to n number. Let's say, for an example, I'm telling you that the peak value constraint, the average value constraint, average energy constraints. So these are some of the sample constraints. With these constraints, if we try to solve this problem, that might result in the nearly Gaussian function.
Okay.
So that's the reason in all the books you will see that the noise is always Gaussian with mean equal to 0.
Mm-hmm. But at the same time, sir, in practical scenarios, the noise that we observe may be a mechanical noise, which is said to be impulsive, maybe short noise, that is internal noise, or maybe a thermal noise that actually is considered to be a WGN for certain frequency range. So in theoretical analysis, we are considering to be a WGN, but in practical, this may not be a WGN. So do you not think that this will create some deviation into theoretical result and result that we are getting practically?
Yeah. So what we need to do is, if if we have a lot of faculties as participants, that's why I told that this is one of the research problem where channel modeling is one of the research problem. So various kinds of channel though have been modeled, but with limited number of constraints. There has to be realistic constraints, and if we go for modeling in those cases, then probably we might end up with the right kind of model.
Okay. Yeah.
The noise can also be non-stationary. So in that case, the model definitely is going to change.
G.
So here the very first assumption we assume is that it is stationary. Right?
Yeah. Yeah. Yes, sir.
This is one reason that it is never correct.
Okay. Okay. But at the same time, sir, there is one more thing that noise is considered to be white, as you have mentioned. So we generally take in our assumption that noise is white, but in practical scenario also, in the same line of argument, noise may not be white or it may be colored rather. So how this practical communication engineer, they basically solve this problem that
Yeah, I got it. So actually, when we consider the noise as a white, it is basically taking a worst view. See, worst case analysis is always the better one as compared to the best case analysis.
G.
In computer science people, they always, give preference, more weightage to the worst case analysis. So what we are assuming is that this noise is white. So it means that it is existing throughout the spectrum. So that is fine, because this is keeping in mind the safety of the assumption. It is a very safe assumption. But at the same time, when we call it as a Gaussian, then we are giving a model name. White is or colored. Okay, white or colored noise. Colored might be a little risky, but white is absolutely no risk. So therefore, we might always consider it as a white noise. But because white noise has to be modeled, then only we can find out some statistical value out of it. Right?
Okay.
Like we consider that the power spectral density of the white noise is n0 by 2. Now, these all questions, have to be, because there has to be some statistical value of this.
Precisely.
So then only we can solve some question. So this is one reason that it has been approximated and considered like this for the normal calculations purpose.
So that means if we have done analysis for worst case, definitely it is going to work for less than worst case. That is a practical scenario.
So colored, it will definitely work.
Yes, sir.
So if it is working for white.
Yes, sir. Yeah, that is right. One more question has come to me that in nowadays in smart communication system, now 4G is there, now 5G is also have come in some of the countries. 6G research in 6G is also going on, especially in Finland and by Nokia. So the question is that what type of detection schemes are being used in modern or smart communication systems?
So that's what I was telling. In between, I said few, I think, lines for that also. I proposed, why I'm proposing this topic is because it is statistical and intelligent communication system. Yeah. Statistics means it is leading to later on an artificially intelligent receiver. Because artificial intelligence is also statistics based. So therefore, slowly, I didn't call it a AI based, okay, because I'm not using the AI concept, but I'm using statistics, and further I can extend it to AI, the same statistics concept, so that later on, nowadays, where maximum part of the communication is intelligent. Okay, so that is not existing in hardware, it is existing as a software. So like the companies, former companies at our times like Hughes and all that, they used to write the communication software, and they needed communication engineers for that. I think Hughes has a new name nowadays. I'm not just getting it. So those companies used to target at our time the futuristic receivers, because nowadays the receiver has to be intelligent not only in tackling the errors, intelligent way of correcting the errors, because error correction is now also intelligent. At the same time, the kind of content which is being delivered through the communication, kind of content. Like for example, I tell you, I tried to solve one problem, which was a research problem. And this is also good for the new researchers whom we wish to take. Like for example, terrorists are using IP phone for communication. Now what happens is, normal communication is through a particular channel, but IP packets, nobody knows when the first packet has reached the test, when the second will come. There is no continuity in that. So what happens is that it is not only difficult to collect the whole speech, but also to detect the anti-national paragraphs or the text or the spoken words in those data transmissions is going to be a difficult task. The reason being, what I was told is that they are not only using the IP phones, but also they are trying to encrypt the information which they are transmitting. And that encryption is a haphazard, unknown encryption. Like A is like a Z, B is like a C. There is no regularity in that. So how can we detect the voice? So what I did is, we try to recognize, I'm not telling that method to you because that is a research part given to the defense already. So, but I'm telling you what is the outcome of that. Outcome is in terms of that we could find out, we could separate out the speech packets from rest of the data set. There are billions of packets being transmitted. Out of that, we could separate out the only speech packets. So this was a good outcome, and we got almost 70% success in that. So from those broken pieces of speech packets, we could get the information out of it. Yeah. What they are speaking also, that haphazard encryption, that was a second part of the research, which we didn't carry out. My job as a communication person was to separate out the speech packets from the IP packets. So this is a very beautiful thing. So similarly in communication, if the communication is intelligent, then we can do and employ large number of statistical intelligent algorithms, methods on the received signal. So this is a big, beautiful thing.
Yes, sir.
As compared to the old style receivers.
Yeah. So there's two more questions. One question is, what is the best book you think for communication engineering for fundamentals?
Okay. Fundamentals as such, many people as such study Hakins also, but the information content is not given incomplete in that book.
G.
It's just the very glimpse of the information,
G.
though given correctly. Okay.
G.
And there are certain foreign authors' books, but what I propose to you is, like for example, when you have to study the analog modulation,
G.
some amplitude modulation and all that,
G.
the best for the Indian context, which we used to follow earlier, but somewhere we have stopped, and we are taking some easy-going books by some local authors,
G.
which have n number of errors. So I suggest that please don't follow them. Follow the original research papers, because you just have a look at the amplitude modulation, which you study in the books and which was in the original paper. The original paper has explained it in a very, very nice manner, in a very detailed manner. And there are many concepts which are not at all in any of the books. There is a book, though, by, I think, Taub and
Schilling.
Yeah. So that is also a good book. But again, the thing is that many of the students may not be able to understand. But that book is a correct book. Whatever is given in that is correct. What you study in the local author books is incorrect. So always refer to the book by a good author. Don't go through how many numericals which have been mostly copied or from elsewhere. These are part of it. So students should go for a best author book or research papers.
Okay.
Right? Take the research papers. That is the best.
Tobin Schilling is being followed as a reference book for Principle of Communication course that is in 5th semester.
Yeah,
so,
that is the right one.
Yeah. And one more book that we are following is a BP Lathi in the 6th semester for digital communication.
Yeah,
and,
that is also fine.
Yes, sir. Okay.
That is also fine. It doesn't have errors.
Yes,
it's
sir.
not like he's not a local author. So he is fine and good.
Sir, one last question from you, that which software are being used for simulation of communication engineering system?
Yeah. So best thing will be, if you want to have a practical, then go for using your algorithms on the embedded system. If you can establish that kind of laboratory. If it is not possible, then try to design small hardware. And this all I try to implement at DTU itself. There is another way of taking up. See, if you go for simulation softwares like, in general, we go for this MATLAB. I've seen, so many places. But that's not the learning. It's a learning of a program. It's programming which you learn. But how will you learn the communication is a different thing. So what you need to do is you need to have a breadboard and you need to have a software. Right? If both the things are along, then that is the right way of doing the practical.
So you mean to say it should be a combination of hardware and software to better understand?
Anything simulation only is of no use.
Yeah.
At least of not much use. It will be just a, giving some glimpse of that there can be some practical like this. More or less students, they download and they cram it. It's nothing, it's a programming they learned. Using a toolbox doesn't mean learning communication. That's only learning MATLAB or some kind of software. So better not to use these softwares, especially. You go for some specialized hardware, and hardware, most of the designs are on the hardware, and only display and acquisition of signal is through the software. So this system, if it's possible, can also be designed. I had been, using my own system also here in the laboratory, at least in some of the laboratories. So what I suggest is, if there is a team of faculty and students, if there can be some system over there at your college and at any other college, participants are from other colleges also, and I can always help you to come out with such kind of products.
Definitely.
Right? So you have your own, just say, there is a concept of the, Atmanirbhar Bharat also. So you have to design yourself and then teach based on that, because that will be the right teaching. Otherwise, these platforms are, not very, very useful. I've seen, for so many years, the students have been rather wasting time in the laboratory and they have lost interest in the laboratory. There is almost nothing to do with there. Right? With the kits, never purchase the kits. These kits are absolutely of no use because the student doesn't learn anything. Breadboard and the data acquisition board and then the computer. This is what you require, and no ready-made kit. Give the input and take the output.
Yeah. Right. Thank you very much, sir, for your knowledge sharing. Really, it was very informative session. I'm getting feedback from the participants also. And thank you for being part of this webinar. You have given your precious time from your busy schedule. So I wish and hope that we will meet again on some other topic sometime later with you as a speaker.
Sure. Welcome.
Yeah. Thank you very much, and thank you to all the participants.
Okay, all the best. All the best.
Thank you very much, sir, and thank you, Vishwashi. Thank you very much for providing backend support and all the ISF members. Yeah.
Thank you, sir.
Yeah. Thank you to all the student members who are who had been instrumental in making this webinar a success, and keep doing the similar way. Thank you very much.